covered almost the question in the final, because chapter 4 ialah combinational logic circuit and combinational logic gates, which we have part 1 and part 2. So you can review and study daripada study daripada video tu ya, untuk chapter 4 part 2. Okay, so yes, let's start the chapter 5, where we will learn again still the combinational logic circuit, but now we want to see what is the application that can we derive, or can we what can we design from that combinational logic circuit. In chapter 4 part 2, you have learned about the XNOR gate, XOR gate, and how NAND and NOR gate can be the universal gates for all the universal gates, right? So in chapter 5, we will see the application from chapter 4, part 1 and part 2. Okay, in this chapter we'll cover adders, comparator, encoder, decoder, multiplexer, demultiplexer, and the parity generator or the parity checker. Okay. Okay, MSI, medial scale integration, describe the integrated circuit that have from 12 to 99 equivalent gates on the chip. They include a logic function such as counters, shift registers, arithmetic logic circuit, encoders, decoders, comparators, multiplexer, demultiplexer, and the other combinational sequential logic circuit. And what is the advantages that such device exists is we want to make the lower cost of chip, higher reliability, and design simplification of complex logic system. Alright, so this arithmetic logic circuit here refer to the adder and the subtractor, okay, subtraction, okay, or subtractor. Alright, so let's see the first one, which is adders. So an adder or summer is a digital circuit that perform addition of the number. And in computer structure and other kinds of processor, adders are used in the arithmetic logic units to calculate address and table indices and for many similar operations. So adders sama juga dengan summer, right? Sum, it's not the summer weather, it's sum. Okay, arithmetic logic. All right, so what is the half adder? For the adder, we will cover two types of adder. First one is the half adder, and then the second one is the full adder. Okay, where the half adder accept two binary digits on its inputs and produce two binary digits on the outputs. Okay, kalau okay, you can see here, this is the logic symbol of half adder, okay, or the block diagram of the half adder. Okay, for the half adder, we got two input bits, for example, number A and number B, and then two output, which is a sum and carry, right? And we can see the operation of a half adder like in the truth table. And for the half adder, you need to recall how the basic rule for binary addition that you already learned in chapter 2, if I'm not mistaken, or chapter 1. Okay, so let's see how what the half adder works, all right, to do the summation and summation in the arithmetic logic. All right, so for two digits, okay, or for two inputs, we know that we will have 4 possible input. Yang ni yang biasa. Kalau dia cakap half adder, it's automatically 2 bits and with 4 input variables. Okay, 4 possible inputs. Okay, because we want to add 2 binary digits. All right, so the input will be 00, 01, 10, and 11. Okay, so how can we add? So it's same as in the in the chapter 1 with the basic rule for binary addition. So 0 plus 0, this is the summation, summation or the sum, and this is the carry, right? So as for the sum, we know that 0 plus 0 is equal to 0 with the carry also 0, and 0, 1 is equal to 1, also the carry will be 0. 1, 0, the output will be, or the summation or the sum will be 1 with the carry 0, right? And then 1, 1 is equal to 0 with the carry output of 1. So this is the truth table for the half adder. And then what is next? You need to construct the or to come out with the Boolean expression. Okay, this is the Boolean expression for the half adder. So in order to come out with a half adder Boolean expression, you need to construct the K-map. All right. So this is a K-map. Seperti yang kita belajar sebelum ni, K-map kita hanya tengok pada bila masa the output is 1. Okay. So for the half adder, because we got 2 output, so first you need to have the K-map for the summation, for sum, right? So we have A, B with 0, 1 and 0, 1, and then only when A is equal to 0, A is equal to 0, and B is equal to 1, the output will be 1. And then the other one will be when the A is 0, A is 0, B is 1, B is 1, A is 0, B is 1 here, and A0, okay, A1, A1 and B is 0 is equal to 1. All right. So this is, and then from here, you need to come out with this, the group or circle, and make sure you know how, what is the rules for circling the one. The minimum number of one is 1, and the maximum will be 8 or 16. All right. So for the first circle here, you will have A and B bar, because B is 0 here. And then for here, you have A is 0, A bar, and B. So the output will be A bar B plus A B bar. All right. So this is coming from the theorem algebra. I don't remember which number of the theorem, where you can simplify A bar B plus A B bar B, A bar B plus A bar B bar is equal to A XOR B. All right. The exclusive OR. Okay, the sum can therefore be expressed as the exclusive OR for the input variable. So this is the first AND gate. Okay, this is first AND gate. This is second AND gate, and you combine these two gates with the OR gate, or you can simplify in this version or in this form. Okay, and then you this is for the sum. Okay, this is for the sum output, number one. And then what is the Boolean expression for the carry output? So the carry output only when both A and B are 1, the output will be 1. So A are 1, B is 1. Uh, so the output here will be 1. So you will get the expression for the carry output will be C out will be AB, right? So we have here two equation, one for the sum and the other one is for the carry output, right? All right, so we know that this is coming from the equation 1 and this is from the equation number 2. So after you got the expression, the Boolean expression for the half adder, you need to construct or we need to design the logic circuit for the half adder. So the first one or the summation is equal to A XOR B. Okay, so this is the XOR gate. That's why I told you that you need to do a revision on my uploaded video on chapter 4 because in chapter 4 part 2 we will learn about the XOR gate, NAND gate and NOR gate. Okay. All right, from equation 1 and equation 2, the logic implementation required for the half adder function can be developed as shown below. Okay, the output carry with AND gate. So this is output carry with AND gate with A and B as an input, and the sum output is generated with exclusive OR gate. So this is the half adder. Okay, the first example of the combinational logic application. Any question? Are you guys still there? Nur, yes, Amalin? Amalin, Aisha, are you still there?
Yes, madam.
Faham All right, so let's see what is the full adder. If you need to add 3 bits or more, you need to have the full adder instead of the half adder because full adder we will have in full adder we will have 3 inputs and 2 outputs, and the input for the full adder it is same. This is the input bits A and B, but with addition of the input carry. So because the full adder got 3 input bits, so we can add the 3 bits or more untuk tambah sesuatu nombor. As for the output, they are still same with sum and output carry. Right? And how to do the operation of the full adder, the operation of the full adder. This is full adder, not half adder. Okay, again, you need to write three bits. 3 bits mean 2 to the power of 3. You will have 8 possible input. Okay, 8 possible input from 000 until 111, where A and B is the input variables, and you will have another column for carry in, which is normally we write as C in, and then for the output we will have 2 output. One is carry out and the other one is the sum. And then for the addition, it is same as in the the binary adders. Just you have multi bits. Okay, you have another additional bit here. Okay, so how to do the summation or adder here is, okay, let's see one by one. So 0 plus 0 plus 0 is equal to 0. So the carry will be 0, right? And then 0 plus 0 plus 1, the output will be 1, and then without the carry, same as 0 plus 1 plus 0, output will be 1, and then also the carry will be 0, all right? So now let's see the condition where we will have the carry. So 0 plus 1 is equal to 1, and then 1 plus 1 is equal to 1 plus 1 is equal to 0, 1. So this is the sum and this is the carry. So the sum will be 0 and then the carry will be 1. And same as 1, 0, 0. Here is 1 and 0, 1, 0, 1, 0 with carry output 1, 1 plus 1 will be 0, and then we'll carry 1, and then lastly we have 1 plus 1 plus 1. Okay, 1 plus 1 plus 1, you will have the 10 plus 1, so 11. So this is the sum is equal to 1, and then the output for carry will be 1. So this is how you add the 3 bits using the full adder. Yang ni clear eh? Any question regarding the adder for 3 bits number? Hakim, faham? Hakimi, sorry, Hakimi.
Faham, Puan?
Faham eh? I afraid that you guys will be sleeping during my class because I can't see. Maybe next time we will ask you to open the video, okay, so that I don't feel that I am alone in the class. All right, let's see. So we got this truth table. Okay, this is a truth table from the full adder. Okay, where we have A, B, and C in as the input, and then two output here, and from the sum. Okay, let's see what is here. 1, 2, and 3, 4. 4. Okay, let's draw the K map for the sum first. Okay. So we have A, B, and C in. Okay, it doesn't matter where or you want to write A, B, and C in or A and B, C, right? So this is 0, 0, 0, 1, 1, 1, and 1, 0. And then remember to have the gray code for the bits more than 2 when the input is more than 2, right? So okay, let's see, the output will be 1 when A is equal to 0 and B, C equal to 1 and 0. A is equal to 0, 1, 0 is equal to 1, and here is A is 1, sorry, this is 0, this is 1, okay? When A is 1 and 0, 0 is 1 here, and then we have 0, 0, 1. 0, 0, 1 is 1, and lastly 1, 1, 1, 1. Okay, right. So this is the what the K map for the what for the sum. Okay, if you found or if you trigger this kind of diagonal loop or diagonal group, you can straight away write this is mean XOR. Okay, so it's equal to A plus B plus C. Okay, ataupun this is how you come out for the Boolean expression from the K-map. And you also can get the expression from Boolean expression from the truth table. Okay, and remember last time I think I pernah bagi tahu biasanya the question will ask you first to come out with the Boolean expression from the truth table, and then you need to reconfirm with the K-map. Okay, so in order to see whether you will get the same answer or not, right? Okay, so let's see if you write the expression from straight away from truth table. So this is A bar, B, and C bar. A bar, B, and C bar. Okay, this is the first one. The second one, you will have A, B bar, C bar. A, B bar, C bar. Right? This is the second one. Third one will be 0, 0, 1 will be A bar, B bar, A bar, B bar, and C. This is the third one. And the fourth one will be A, B, C. Okay, A and B and C. Okay, so simplify this expression to get the final Boolean result. Okay, so you can use the theory from the theorem Boolean algebra. So A bar, you boleh kumpulkan so keluarkan A bar. So this is the first, right? So you will get A bar, B bar, C in plus B, C in. Okay, this is coming from 1 and 2. And then the second term will be kumpulkan A, because you got the similar variables A here with B bar C in plus B, C in. Okay, and then this is when you got one of the variable is bar and the other one is not, you can simplify it as the exclusive OR. And again, same as here, you will get A bar, sorry, A, B, C in bar. Okay, and from this expression, you will be simplified to get the A exclusive or B and exclusive or C. Okay, and right, so here is A exclusive or B plus A as exclusive or C for the sum input, right? And then for the carry output, so you see there are 4 of them, 1, 2, 3, 4 for the carry output. Let me change the color. Okay, so let's see, the first term will be A, B, and C bar. A, B, and C bar. Carry output. A, B, C bar. Where's A, B, C bar? Okay, this one. Okay, this is A, B, and C bar. The second one will be A bar, B, C. A bar, B, and C. Okay, the second one. Third one will be A, B bar, C. A, B bar, C here. And the third one will be A, B, C in. All right. So again, you need to simplify this Boolean. Now we have A, B, and then C in bar plus C in. Okay, yang ni Okay, so you cancel this, you will get the first term here. Now the second one will be AB C in plus AB C in. Okay, here you have sini A adalah bar, and then for the third term we have B bar. So we can exclusive or A and B. Okay. So the final output will be A, B plus C in times by, or C in AND gate of A plus A exclusive B bar. So you will have two output here, one for the sum and one for the carry output, right? So this is carry output. And therefore, two full adder equation perform one possible circuit as shown here. Okay, kalau kat sini daripada expression, boolean expression ni, you can build the circuit. Okay. Alright, so as for this circuit, okay, let's see. The first one will be A exclusive B and exclusive C. So, and remember, in order, normally we draw the logic gates with two inputs, okay? A and B only, unless the question mentioned that the gate R, or the gate is with three inputs. So for the first one, we have A and B. Okay, A and B here, XOR gate. This is first XOR gate, so you will get the output of A XOR B, and then you will have the C in here. Input number 3, C in XOR, you will get the output of sum. Okay, for the first one. So this is the sum output. Okay, and then as for the carry output, you will have, let me, all right, so the first one, so this is the output for the carry. So you will have AB. So AB is equal to AND gate. Okay, AND gate, the first AND gate, G1 for AB, and then the second one AND gate for exclusive or B with C in. Okay, this is gate number 2 for the exclusive OR, and you have the C in here with the output for A XOR B, and then it will be combined in the combined using the gate number 3, which is the OR gate. So you will have as for the output yang kat sini, for the summation and the carry output, you don't need to to sum them, because it is the different output. Ada soalan? Faham tak? Tan Xiao Xiang, are you still there? Hello, hello. Nur Adila, can you hear me?
Yes, madam.
Okay, faham Wahidah, Nadira, boleh faham? Let's see how many people are here.
Yes, madam.
48 people. Ashraf Imani, are you there? Where's Ashraf?
Yes, madam.
Okay, all right. Thank you for the response. Give me 1 minute. Okay. Okay, now let's see when we have three or more adders. Okay, kalau tadi kita hanya nak tambah dua nombor saja. Okay, ataupun satu nombor. Okay, with 3 bits. How about we want to add uh, 3 or more numbers using the binary adder. But before that, okay, alright, full adder also can be implemented using two half adder or one gate. Okay, kalau kita tengok tadi half adder, for the half adder, you will have this logic diagram with one XOR gate and one AND gate. So if we combine these two half adder, okay, this is half adder number one, half adder one, and this half adder number two with the OR gate. So you will have the full adder. Okay, full adder also can be the combination of two half adder and one gate. Okay, but this is for carry. For the sum will be from the XOR. Okay, because we will have this AB, this is A XOR B, and this output will be the second input for the XOR gate, and then we will have A XOR B and XOR C. Okay, so this is for the sum, and then for the carry output, you will have the input of AB here, and then AB plus C in here, C A XOR B. Okay, and then you combine with the XOR gate. So carry output will be AB plus C in A exclusive or B. Right, so this is the other configuration for the full adder, right? So with the block diagram as in below's figure. Okay, and next, right, so when you have n bit parallel adder using it can be constructed using n full adder with zero carry in on the LSB. So what is the LSB? It is the least significant bit. Okay, maksudnya bit yang paling rendah. And then we know that for 2-bit numbers, 2 adders are needed. For 4-bit numbers, 4 adders are used, and so on. Okay, so for example, if we were to add up the binary numbers of 1011 and 1000, okay, so let's call this as number A, and this is B. So we would need 4 adders in total because the n length of the larger number is 4. And in general format, addition for 4-bit numbers is like this. Okay, this is the general addition that you already know how to add 4-bit numbers. But to represent in the half adder or in the full adder, so if your number got 4-bit, so you need 4 full adders, right? Okay, let's see. So this is A start daripada kanan ialah LSB, A1, A2, A3, and A4. And this is the number B, B1, B2, B3, and B4. Okay, make sure if you want to rearrange the adders. Okay, now let's see how can we arrange four adders parallel to each other. The first one starting from the LSB, the least significant bit, and this is the MSB, the most significant bit. Okay, starting from A and B. So sebab kita kat sini kita ada tiga input sahaja, A, input B, and input carry, and with the two output. Okay, for the output, we have the what the sum and carry output. So you need to arrange A1 need to be added with the B1. Okay, A1 and B1. So here you have A1 and B1 with the carry in. Kat sini masih belum ada carry sebab kita hanya ada dua bit sahaja. So the carry in here is equal to C0. And then the carry output will be the input for the carry in for the second half adder. Second adder or second full adder. Okay, A2 need to be add with the B2 with the carry, which is from the carry output from the least significant bit, and so on. Okay, carry output ini akan jadi carry input for the next adder, and finally you will have the final sum, which is the E ataupun summation 4 with the carry output will be the summation number 5. Okay, so this is the block diagram for 4-bit parallel adder using 4 full adders. Okay, so yang ni kita akan apply ataupun the application will be see or shown in the lab 4. Right. Alright, so this what I told just now. And then if you need to write the logic symbol for the 4-bit parallel adder, the first binary number is binary number A, and then this is binary number B with the carry input here. And then you will have the output for 4-bit summation or 4-bit sum with one carry output. Okay, and this is the general format for 2-bit numbers. Right, this is the example of IC pin or IC for with 4-bit parallel adders, which is 74LS283. So this kind of IC gate you can find in the lab. Okay, sebab sekarang kita akan buat lab secara virtual, so you only you will not see the real gate for 4-bit parallel adders, but if you see the gate of 74LS283, ia adalah adder with 4-bit parallel. Okay. Alright, so let's see exercise 1A. Okay, so we've referred to the figure. What are the values for A1, A4, A1 until A4, B1 until B4, C1 until C4, and sum 1 until sum 4. So what you need to do is first to draw this logic diagram of 4-bit parallel adder. Okay. Then question A, the binary number 9 is added to binary 3. So first you need to transform or to convert into the this is decimal 9 and 3, convert to the binary of 0 and 1. So as for 9, you will have it to the power of 0, 1, 2, and 3. So 8 plus 1 is equal to 9, plus 2 the power of 2 is equal to 2 plus 1 is 3. So this is how you rearrange into the general addition operation. Okay, this is uh, the what the format, and then you have 10010011. Okay, the first carry will be the carry in. Okay, here carry in will be 0 lah, sebab kita tak buat apa-apa lagi. Okay, and then again 1 plus 1 is equal to 1, is equal to 0, with the output or the carry will be 1. So this 1 will be the first carry. Okay, carry 1 ialah the carry output here. C out, C1 will be connected to this. C0, C1, right? And next is C1, C2, C3, and C4. Okay, and then 1 plus 1 is equal to 0, with second carry will be C2 is equal to 1. Okay, C2 is equal to 1. And 1 plus 0 is equal to 1. Carry here is equal to 0. Okay, and then 0 plus 1 is equal to 1. And then C4 will be carry out also will be 0. Okay, so you will have 4 sum. Okay, 1, 2, 3, 4, which is 1, 1, 0, 0. And then the carry 4 will be the summation number 5, with the output will be 0. Okay, so you can do the exercise B, where you need to add 7 and 6 using the parallel 4 bits adder, 4 bits parallel adder. Okay, alright, so kalau tadi kita ada 4 bit adder, now you want to add more bits and more bit. Okay, so adders can be expanded to handle more bits by cascading. What is cascading? Is to put next to each other, and for a 4 bit adder can then be combined to form a higher bit adders, and so on. For example, two 4 bit adders can be combined to create 8 bit adder. Okay, so kat sini kita ada, so for example, this is 2 bit adder. Okay, a 4 bit parallel adder. Okay, with A and number B. Okay, kalau kita nak tambah the numbers with 8 bit adder, so you need to by cascading two 4 bit adders, you can create the 8 bit adders. So the number A will be from A1 until A8. Okay, but separately, in separate adders, because 1 4 adders only can handle until 4 bit. Okay, and then for the number B, we have B1 until B4 for the first adder, and then B5 and B until B8 for the second 4 adder. Okay, 4 bit adders. And remember, the least bit must be always on your left. Sorry, on your right. All right, and then this is the MSB on your left. Okay, and suppose we want to add two 8-bit numbers. Okay, and the process is same. 1 plus 0 is equal to 1 with the carry 1 here. 1 plus 1 is 1 with carry 1 1 1 1 1 1 0. Sorry, 1 0 1 0 is 1, no carry. Sorry, again 1 0 is 1, carry ialah kosong. Again 0 1 1 0, and 0 1 1 still 0, 1 1 0 1, and here is 1 with carry 1 0 1, and 1 0 1 and 1 1 will be 0 with carry 1. Okay, so the output will be, this is the sum from sum 1 until sum 7. Okay, 1, 2, 3, 4, 5, 6, 7. And then the last one will be the carry output ataupun the sum number 8. Okay, and the process of connecting the carry out from one adder to carry in. Okay, this is a carry out to the carry in. Okay, to the of the next adder is referring to the cascading. Alright, so this is how we want to add two numbers with the 8 bits. Alright. Okay. We also can expand until 16 or 32 and so on. Okay. So you need to add more 4-bit adder lah. Okay. Ni daripada 4 untuk 8 and then this will be 16. Okay. So this is 4 times 2 and this is 4 times 4. So you will have 16. Okay. Akan ada juga 4 times 8 adders. So you will have 32 inputs. Alright. So this is the adder for subtraction. So for summation, and for the subtraction, we will have the parallel subtraction using parallel adders. Okay. Parallel adders also can be used to perform subtraction. For example, A minus B using the 2's complement system. Okay, the bits of the subtrahend B are inverted and carry in CO is equal to 1 to produce the 2's complement. The design subtractor using parallel adder is shown in figure below. So for the example, for the subtraction using parallel adders, we can see in the lab also. Okay, so contoh A0 will be A0 minus B. So this B, you need to put the bar. Okay, means that it's inverted output of B register. Kalau B, first B ialah 0, so it will be 1. Okay, the inverted. Alright, so the C in ataupun the C out is equal to 1 to produce 2's complement. Okay, so nanti kita akan tengok contoh for the subtraction using the parallel adders. Alright, so what is ripple carry adders? Is one in which the carry output of each adder is connected to the carry input for the next higher order stage. So this is how, for example, if you have 4 numbers, 4 numbers with 2 bits that need to be add. Okay, so you have 0, 1, 0, 1, 0, 1, 0, and 1, 1. You want to add these numbers using the half adder. Okay, any adder lah. Kalau 2 bits number, you need to use the half adder. Sorry, the full adder. Alright, so this is A1, B1, A2, B2, A3, B3, A4, B4. Okay, so when you arrange the adders next to each other, we call it as the ripple carry order. Okay, the sum and the output carry of any stage cannot be produced until the input carry occurs, and this causes a time delay in the addition process. Okay, bila you tambah 4 nombor ni menggunakan these 4 carry adders, you will get the propagation delay. Okay, this delay is called the propagation delay. So kalau satu adder akan menghasilkan 8 nanosecond of delay, So if you have 4 adders, so you have in total 32 nanosecond of the carry propagation delay. All right. So we can speed up the addition process by eliminating this ripple carry delay is called look ahead carry addition. Okay, this is the other technique to speed up the addition process. Right? Any question until here? Fadil?
No.
No, eh? Azizi, are you still here?
Yes, ma'am.
All right, okay. Faham, eh? Okay, let's proceed to the next combinational logic, the application, which is the comparators. Okay, the comparators is the basic function to compare the magnitude of two binary quantities, and it is to determine whether those two numbers are equal or not equal. All right. So first one we have the equality. Equality maksudnya kita nak tengok nombor tu adalah sama, alright? Sama atau tidak. So using exclusive NOR gate can be used as a basic comparator because it's the output is 0 if the two inputs are not equal and 1 if the input are equal. Okay, yang ni you boleh refer back to the chapter 4 part 2 where we discuss about the XNOR gate. Okay, the XNOR gate output will be 1 when only the inputs are same. Okay, so the input are same here, the output will be high or 1. Okay, and if the inputs are not same, not equal, the output will be not equal lah. Okay, so the idea is, for example, if we all right, to compare the equalities of two-bit binary number, an addition of exclusive NOR gate is necessary. So, for example, you have the two number that you need to compare. Okay, for example, A is equal to, let me change. Okay, A is equal to contoh lah Kau ada contoh kat sini? Yes. Let's see the example. Alright, so we have number A, which is 1, 10, 1, 0, and 2 for A. So this is A1, this is A2 or A0 with the A1 here. And then for B, we have the 1, 2, 1, 0, and 2. Okay, so this is B1 and this is B0. Okay, so kalau kita tengok secara as a human, we know that this A and B are same, right? So ini adalah A adalah 10 and B adalah 10 in binary. So of course they are same. So how computers can compare these two numbers? So by using this XOR gate, so we can compare either these two numbers are equal or not equal. Okay, let's see. So using XNOR gate with N. So A0 start the first the upper gate, the gate number 1 will start with the LSB, and this is the MSB. Okay, so A0 is equal to 0, B0 is equal to 0. All right, A1 is equal to 1 and 1. So again, using XNOR gate, we know that if both inputs are same, the output will be high or the output will be 1. Okay. So again, to to combine or to compare both two numbers, we need the gate number 3, which is the AND gate. So 1, 1 is equal to 1. So if the output is high, it is equal, right? So number B, so we have 11 for A. So A0 is 1, A1 is 1, B is 10. So this is 0 and this is 1. So compare this, 1, 0 will be 0 because the input are not same. 1, 1 is 1, so 0 and 1 is equal to 0, which is low, and we know that this A in B and B in B are not same. Okay, kalau kita tengok secara dengan mata kasar, kita automatically akan tahu these two numbers are not same. Okay, but how computers compare then? Compare these two numbers by using this solution using the XNOR gate. Any other question for this comparator? Tiada. Zul Afif, ada soalan?
Ada.
Tak ada, senang kan? Okay, kalau tadi kita nak check sama ada dua number tu adalah sama atau tidak. So how can we check the number is inequality or not? Okay, so many IC comparators provide additional output that indicate which of the two binaries are being compared. So for example, A is equal to B. So inequalities yang ni kita dah discuss lah, as discussed in the previous section. This is 5. But how can we compare whether A is greater than B? Okay, and then A is less than B. Okay, this is the logic symbol for 4-bit comparator. So to determine the output, we need to examine the MSB first, the most significant bit first. Kalau kat sini dia ada 4-bit numbers, and then we need. Sorry, do you have question? If you don't have question, kindly mute your microphone, please. Alright, to determine the output, you need to examine the MSB first. When such an inequality found, for example, we found that A is not same as B, the relationship of the numbers is established. So, and then any other inequalities in lower order bit position must be ignored. Okay, untuk check the inequality, so you only need to consider the MSB. Let's see the example of exercise 3, where we have this number A with A0, A1, A2, and A3. This is B0, B1, B2, and B3. Okay, rules tadi cakap we only need to consider, first we need to consider the most significant bit. Okay, MSB here is A3 and A3 and B3. So A3 is equal to 0 and B3 is equal to 0. Okay, sini kita dapat A3 is equal to B3. So it is equal, not inequality. So we need to see the next MSB, which is the A2 and B2. A2, B2. So berapa A2? A2 is equal to 1 and B2 is equal to 0. So here we know that A2 is bigger than B2. A is bigger than B is here. So only when A is bigger than B, the output will be high. So yang lain kita tak perlu tengok pun, kita just ignore. Okay, but you can still check whether others are in quality or not. So let's check A1 and B1, where A1 is equal to 1, B1 equal to 1, 1, 1. Okay, so A1 is same as B1, and for the A0 and B0, we have B0 is 1, A1, sorry, A0 is equal to 0, and so this is A will be small, A is smaller than B, but sebab ini adalah the LSB, so the output still will be 0. We only consider when the MSB what shows inequality. Okay, so jawapan kat sini ialah A2 is bigger than B2, because from the rules we determine the inequality, you need to examine the MSB first. Okay, and then if you found the inequality, and you already established the relationship of the two numbers, and any other inequalities in lower order bit position must be ignored. Okay, you only can get one final answer for each of the logic diagram. Okay, for each of number. Okay. All right, so this is the example of IC. Okay, 4-bit magnitude comparator. Bit numbers are in the parentheses. Okay, so if you want to compare two numbers, you need to use this IC 74H C85. So that if you have, for example, 0001, and then B is 1011. So you do again how I did just now to compare this A and B, and then only when but see first tengok yang paling MSB, the most significant bit, and then if you didn't find the inequalities yet, follow or refer to the next upper bit. Okay, where you compare here and here. Kalau kat sini kita boleh tengok A is lower than B. Okay, so only when A is less than B, the output will be high. Okay, or 1. Okay, others you can ignore it. Okay. All right, this is another example to compare the 8, okay, 74C85 to compare the magnitude of 2 bits numbers. Okay, 2-bit numbers still okay, this operation requires 2 4-bit number, because 8 bits you need to have 4 bit of the comparator. Okay, the operation is still the same, and then you need to compare from MSB to LSB, and then if you find the first inequalities in MSB, so the output will be high here. Okay, this is for comparator. The other example of the comparator with okay, this sama this is only a 2-bit binary where we have A1 and A0, B1 and B0, and A and B are in the decimal. A and okay, yang ni boleh tengok and when only the output when A is bigger than B, so it's high. Okay. The system is high when A is greater than B. Okay, kita tengok sini. Kalau A0 compared to B0, B1 to be compared to A1. Only when A is bigger than B, the output will be 1. Okay. So, but make sure you only see the MSB. So MSB here is A1. So A1 is bigger than B1. Okay. A1 is bigger than 1. The output will be 1. Or any, sorry, A1. Okay, to compare 2 bit, both, so it's doesn't matter either A1 or B1. When A is bigger than B, the output will be 1. So kat sini kita tengok A ialah lebih besar daripada B. So A0 is bigger than B0. Okay. Next is here you compare A1 with sorry, Z. A1 1 is bigger than 0. Next is to compare A1 is 1 is bigger than B1. Aha, okay, I know that. Okay, now you see the first is B1. Okay, and next is A1 is bigger. Ni betul, betul juga. Here is also correct. And what else? The condition. When A is bigger, the high. Okay, and A here is 1. Where A1 is B1. And I'm not sure whether this is correct or not. Okay, sebab kat sini kita tengok the A1 is same. Let's see the binary input AB, MSB, the high when is binary represent, yeah, okay, input F is equal to 1 when A is greater than 1. A is greater than B. I'm not sure whether this is correct or not because kalau kita tengok kat sini, ia adalah A1 is equal to B1. Okay, only refer to the MSB, the most significant bit, and also here is A1 is equal to B1. One, 2, 3, 4. 1, 2, 3, 4, 5, 6. I will check this answer again, but I think it is not correct because the condition here only said that when when A is equal, when A is higher than B, then the F will be 1. Okay, so here I'm not sure about this. I will check this again, and I will come out maybe with short notes and upload it to the Ulearn. Right, so but the idea is when you know the condition and then you complete the truth table, and then from the truth table you can come out with the Boolean expression, and then simplify the Boolean using the K-map. Okay, use the simplify F to design the comparator logic circuit. So lastly, you will get the final simplified expression. All right, so from the simplified expression, you can build the comparator logic circuit using the logic gates. All right, so you have A1. Okay, let's say the previous answer is correct. Okay, from this truth table, so you will have A1, A0, B1, and B0. So here is A1 with B bar as an input. Okay, this is B bar B, and then this is B bar, 1 bar to be connected to here. This is A. Okay. Alright. Nanti you try to design yang ni. Alright. So that are for the comparator. Next we move to the decoder. Okay. Decoder, encoder, we have another 5 application. We have decoders, and then the complement for decoders is encoder, then multiplexer, demultiplexer, and last one is parity checker. Okay. Alright, so what is the decoder? It's a logic circuit that accepts a set of input that represent a binary number and activates only the output that correspond to the input number, and the rest mean inactive. It's mean that decoder is to choose which it's decode. Decoder is decode. You want to decode, for example, from binary to decimal, for example. Kita akan tengok satu-satu contoh dia. Okay, input is n bit codes. Alright, this is an input, and the output is to the power of n. Alright, so like shown in the figure for line to 16 line. Kenapa? Sebab 2 to the power of n. So n here is equal to 4. And here is equal to 4 is equal to 16. The output will be 16 here. Okay, 204 sama dengan 16. And active low is the activate output line 0 and the rest are 1. And active high, the output line will be 1 and the rest are 0. So for the output, it's either in active low or in the active high. So if in active low, the output will be 0 and the others will be 1, and then in the active high, the output will be high and the others will be 0. For the decoders, we have the extra input, which call it as enable input. So the enable input must be always on for decoder to function. For example, we have the binary decimal code to decimal code decoder shown has active low enable. Active low because here enable dia adalah kosong. Okay, so it is active low. When the pin is low, the coder operate as expected. So maksudnya output dia pun adalah active low lah. Semua ini adalah kosong unless satu je yang akan active high. Okay. Otherwise all the output are 1 because the active low outputs. Hanya satu saja output yang akan kosong. Okay, others are 0 because the enable is 0. Alright, so this is the example of chip number 74H1544, where it has a 4 line with 4 line input with 16 line output. So normally this is input, yang depan tu input and this is the output. Okay, so this is how inside the decoder may looks like, right? And we have the encoder. So encoder sama ada kosong ataupun 1, right? So this is the logic symbol of the chip. Let's see exercise number 1, where you have 4 to 16. Again, 4 to 16 decoder. Okay, from binary to decimal, right? So we know that in binary 10112 is equal, in binary 1011 is equal to 11. So when enable is 0, only at number 11, the output will be 0. Others are 1. Okay. It the encoder is active, but it is in active low. All right. So that's the how decoders work, where you want to decode 1011 to the decimal. It call it as the BCD decoder. Okay, so best binary to decimal decoder. Okay, kalau you tengok ini adalah 11 So pada masa 11 saja output dia adalah kosong. Others are 1. Kalau enable here are 1, so only at here is 1, others are 0. Okay, so you kena tengok dulu enable tu sama ada dia inactive high or inactive low before you come out with the output in decimal. In decimal. Alright, so this is 4 to 10 decoder. Okay, kalau tadi kita ada 4 to 16. Sometimes not all 2 and input combination are needed. This is shown in common decoders below, where we have the 4 to 8 decoder. So not all the time 2 to the power of 4 is equal to 16. Okay, ada juga decoder yang boleh decode from 4 bit to 10. Okay, 10 decimal output. For example, we have here the decimal digit is from 0 until 9, which is 10. Okay, decimal digit from 0 until 9. And what is the BCD code for each of this number? Okay, yang ni again you know, for the 0, the decimal will be 000, and until 9 is equal to the power of 3 plus to the power of 0 is equal to 9. So this is the example of chip 74HC42. Okay, so and enable now is in active low. So if the question asks you to write the decoding function for 4 to 10 decoder, so this will be the output, right? Just write again the output from LSB. This is LSB, and this is the MSB. Okay. All right. So the other decoder example is BCD to 7 segment decoder, and normally we use the 7 segment display as the output. Okay, so 7 segment, why 7 segment? Because this is a 7 segment output. 1 2 3 4 5 6 7, and then we want to see at which output will be lights on. The LED will be lights on. And then again, the decimal digit is only until 9, because we only have one display. So this 7 segment display, we call it as a 7 segment display, can display until 9, 0 until 9. So kalau ada 10 sampai 15, it is don't care. Okay, this is don't care condition. Maksudnya dia tak boleh nak display lah more than 9. Right, and this is the logic diagram for BCD to 7 segment decoder. And how it works, for example, when you want to light up number 0, so all the segment from 1 until 7 will be light or will be high, except for the 0 or G. Okay, so here will be lights on. Okay, for 0. Okay, For 1, only at B and C is light on, or only at B and C is high. And for number 2, you need 1, 2, 4, 6, and 8. 1, 2, 4, 6, and 8. Okay, or we call it A, B, G, E, D, and until the number 9, only at number 9, only at E, it is 0. Okay, sini je tak ada. So you can display number 9. Right? Any question for BCD to 7 segment decoder? Afiq? Is Afiq still here?
Yes, I'm here.
Alright. Faham eh?
Uh,
Shakila? Are you still here? Faham eh? Alright, so let's proceed to next slide. Okay, we've referred to figure below, write the expression of for X and Y, okay, the output. For the inputs A, B, C, D in standard sum of product, can refer to the 4-bit decoder truth table in the next slide. Obtain, okay, yang ni you boleh cuba eh. Okay, for the for the 4-bit decoder, okay, for example, you have 4 binary input, so the output must be in 16. Okay, and then this is the decoding function. You can see at, so here is 0 binary number 0. Only at when the output, okay, only at 0 the output will be 0, others will be 1. Okay, and you can see if you have the diagonal what line here, okay, semua ini adalah kosong yang lain adalah 1. If you see here is 1, so pada masa 1, only at 1 the output will be 0. Here is 2, 2 Now for example, here you have to the power of 3, to the power of 2, 1 and 0 is equal to 8, 12, 13. Tak, 13. Only at 13 is 0. Okay, again this is 16 and here is 15. Only at 15 the output will be 0, others are 1. So this is when the enable is equal to 0, which is the active low. Kalau dia mention the enable is 1, so it will be the reverse so here will be 1, others will be 0. Okay, and so on. Alright, what is the encoder? Kalau tadi kita decode, ni kita encode. So it is a reverse function from the decoder. The process of converting from familiar symbol or numbers to a coded format is called encoding. So for example, we want to encode from the decimal to the BCD. So you have the decimal input of instead of BCD like in the previous decoder. You want to decode, you want to encode decimal to binary, okay, BCD. This is encode. Okay, so 0 and 1, 2, 3, 4. Okay, only at 1 is equal to only at 1 the output will be high. Okay, so kalau kat sini you tengok A0 yang akan high ialah pada input 1, 3, 5, 7 and 9. Let's write. So the output for A0 is equal to either 1 or 3 or 5, 7 and 9. So for A1, tengok A1 kat mana output adalah 1 ialah pada masa decimal digit 2, 3, 6 and 7. Okay, A2 high when here 4, 5, 6, 7, 4, 5, 6, 7. And for the A3 is only high when 8 and 9. Okay, so this is where you implement, okay, implement the decoder, okay, where you need to draw the logic gates from the decimal to BCD encoder. Okay, first you need to come out with this output, okay, and then from this output transform to the logic gates. Okay, for example, at A0 is equal to 1, 3, 5, 7 dan 9. Okay, 1 and we have 3 and we have 5, 5, 7 and 9. So it will be the A1, the least significant bit. And then you can check one by one. I think it's correct. And then for the A3, let's see one more example is the combination either 8 or 9. So that's why we use the OR gate. Okay. Let's see, this one is decimal to BCD and this one is from 8 to 3 line encoder. Okay, from octal to binary decoder where we have the 8 line input with the 3 lines output. It's same. For example, at A1 you find what is the high. So we have A0 is equal to either 1 or 3 or 5 or 7. A1 is equal either this 4, 2, 3, 6 and 7, and A2 is either 4, 5, 6 and 7. Okay, so this is the logic gates for 8 to 3 line encoder. Yes. Next, let's move to multiplexer. Okay, what is the multiplexer? It's basically the data selector. Okay, where you want to select which input that you want to choose for this particular output. For example, so this is the dialer, okay, the data selection. You want to choose either from input 0 until input n. So for example, to display the output I0, so you need to choose the I0. Okay, in order to display the input from I2, so this dialer need to go here, so the output for I2 will be Q will be I2, right? And you need to remember for the output for multiplexer, only one output can be display at one time because we can choose only one input. Okay, set of select input lines, and it directs to a single output line. Okay, hanya satu output hanya boleh dipilih pada satu masa. Alright, so let's see how what is the truth table for 2-bit multiplexer. Okay, so this is the block diagram. Again, each of the gate has their own block diagram. So as for the multiplexer, so this is the first example of the multiplexer where we have 2-bit multiplexer. Okay, mux is referring to the multiplexer. Kalau dalam soalan keluar MUX saja, so automatically you can you know it is referring to the multiplexer. So it has two inputs because this is input. This is 2 is the input and it's only one output to be selected. So input A or input D0 and input D1. And if you have two input, the switch or the selector will be only one. How you know that is by you will have like two log n 2 like that. Okay, so kalau n ialah this is n is referring to the input. Okay, so log 2 is equal to 1. So only one switch or one selector to be have in this multiplexer. Okay, what is the logic expression is coming from this truth table. So the selector will be the input. So kalau 1 bit dia akan ada either 0 or 1. And then if this select the first one, if S is equal to 0, so the output will be A or D0. Next, the output will be if the S is equal to 1. Okay, so this is 0, this is 1. So if the switch select 1, the output will be D1 lah or B. Okay, so this is the the other way to show the logic diagram for multiplexer, where you see here is bigger than here because here you have two inputs and only select one output, and then this is S, A, B, and then this is Z. And from this expression or from this truth table, you can come out with this expression, logic expression, where you have S bar. S is either 0 or 1. So this is S1 and this is the 0. So S bar A, S bar A, and this will be SB. And the output will be SA plus SB. So this will be the logic diagram for the 2-bit multiplexer or 2 to 1 multiplexer. Okay, when you have, so the other example for multiplexer is you have 4 times 1 multiplexer. So this is always an input and this is output. So how berapa selector data select input we have? So how can you find the selector or the select input is 4 to the power of 2 is equal to log 2 times 1 is equal to 2, 1 times 2 is equal to 2. So this 4 times 1 multiplexer, we have 2 input selector, 2 data input. So kalau ada 2 bit, so you will have 4 input variable. Okay, 4 possible input. For possible input coming from 2 to the power of n, 2 to the power of 2 is equal to 4. Okay, from 0, 0 until 1, 1, where the input selected if will always like this, from LSB to MSB. Okay, so kalau input kalau pada masa S1 is equal to 0, S1 and S0 is equal to 0, it always equal to D0. Okay, and when S1 is equal to 0, S0 is equal to 1, the input selected will be always D1 and so on. Okay, so what is the output expression coming from this truth table will be here. Okay, it is S1 bar, S0 bar, and then the input will be selected is D0. And until 111 is S1, S0 times by D3 for the output Y3, okay? And then this is the combinational gates inside the 4 times 1 multiplexer. So from this expression, you can have this combinational logic gates. Any question for multiplexer? Hello, Ruizi? Ada soalan? Are you still there?
Yes.
Do you have any question regarding the multiplexer?
Not yet.
Not yet, huh? All right. All right, so this is the other example. We have 8 to 1 multiplexer. So if you see the type of multiplexer, first you need to find out how many inputs, how many select input are here. Okay, select input. Kalau kat sini kita boleh tahu log 2, 8 is equal to 3 lah. Okay, so they have 3 select data inputs, and then this is the output. All right. So for the 8 to 1 multiplexer, you will have the enable input. Okay, only during only at 8 to 1 multiplexer, there will be the enable input at the logic gates, and then the Y will be is equal to here. So this is the logic, the truth table for the 8 to 1, and we can see the Y is 1 when it is the active high. Okay, others will be 0, which is the active low. And then this is the Y is coming from this expression. For example, when at 0, okay, Y is equal to 0, so you will have S0 bar, S1 bar, and S2 bar times by D0. Okay, this is always D0 until D7. Okay, start from the LSB, the least significant bit at the top, and this is the MSB. Okay, try to find out whether you have the same output with this output or not for the 8 to 1 multiplexer. Okay, this is how you can design the logic, the Boolean expression using the multiplexer. Okay, macam I cakap tadi lah, kalau 4 to 1, hence 2 selectors requires. For the 8, you need 3 selectors. First, you need to observe the numbers of the input, construct the truth table, and then choose the selector. Okay, boleh try to design the circuit for this F. Okay, I want to go very fast. Next is okay, let's try one of the example here. Um, mm, 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 mm. Okay. Okay, logic design using 4 times 1 multiplexer. So you have this output F is equal to blah blah blah. You need to design 4 to 1 multiplexer. So you will have to select input, two selectors. Okay, two selectors. You will have four possible input condition, which is from 00 until 011. Okay, your truth table may look like this. Okay, and then we have FF is referring to the previous slide. This is F, AB, blah 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 blah. So from AB, this AB, from this F, you need to fill in the the truth table. Okay, yang ni pun you boleh cuba buat juga, atau we can discuss it during the tutorial, because I also need to what to show you the to explain about the lab. Right, this is nanti you boleh tengok example multiplexer. Demultiplexer ialah basically reverse the multiplexing. Kalau tadi multiplexer daripada banyak input, you only choose one output. But for the demultiplexer, you only have single input, but you distribute to uh, uh, multiple output. Alright, so again, the selector also based on the input. For example, if you have 1, 2, 4 lines, so for output, we'll have 2 selector. Right, so the logic circuit for 1 line to 4 line demultiplexer. This is the logic gates, and then complete the truth table based on the timing diagram. Okay, timing diagram here, you know that you will have 0. This is 0 and 1. 1 0 1 0 1 0 1, and then this is 0 0 1 1 0 0 1 1. Okay, this is data in. Data in will be data input lah. You have 1 1 0 1 0 0 1 1. Okay, so complete the truth table based on the timing diagram. So this is timing diagram. Okay, so we have 0 0 0 1 1 0 1 0 1 1. Sorry, 0 0 0 1 1 0 1 1. Okay, so you boleh masukkan based on this. So for example, at 0 0, S0 is 0, S1 is 1. What is the output? So D0 will be 1, D1 will be 0, D2 will be 0, 0, and so on. You need to fill in the truth table based on this timing diagram to show how the output will be for the 1 to 4 line demultiplexer. Okay. All right. So lastly, we have the sorry, not charity. It's a parity checker. I think. Okay, you can see. I think in your last, in the you learn, you will get the version with the parity checker. Let me open this. All right, parity generator or parity checker. What is the parity checker or parity generator? It's basically the technology, a simple technology to check whether the bits got error or not. Okay, parity is refer to the error. Okay, kalau error dalam komputer ni sama ada noise ataupun ada error lah. Okay, maybe bits error. Okay. Alright, so it is the technology or the method to detect the error. The error, and then it only can detect one bit, okay, one bit of error. Okay, dia punya kelemahan dia lah. Okay, how can we we detect the error? Contohnya, you ada, let me refer to my notes because I think this is not complete. Okay, let's give another 5 minutes to complete this chapter 5, and then we can proceed to the very brief explanation for lab 4. Okay, so for the parity parity generator, parity is error, error generator or error checker. So it's on you only got either odd or even parity or odd parity. Okay. Okay, if in even parity, it will give you this is the numbers of 1 will be even. Okay, sama ada 0, 2, 4, 6, 8. Okay, and then in the odd parity, the numbers of 1 will be odd lah, sama ada 1, 3, 5, 7 or 9. Okay, the output for even parity will be high at this one, and then in the odd parity, in even numbers will be low for the even and then high for the odd. Okay, so let's see one simple example. Contoh ialah you have the original bits of 110 100. Okay, so by using the even parity, okay, the soalan tu akan define which parity you will use. So for example, this soalan will give you the even parity. Okay, so you need to count how many numbers, how many 1 in this bit. Okay, so you have 3. Okay, you have 3 in here, so you know that this will be an error, because kalau even parity, the number will be the number of 1 will be even instead of 3. Okay, so if you need to add an even parity, so it will be, this is a parity bit. So kalau nak jadikan dia even, so you need to have the 1 here. Okay, so now if you want to repair this bit, the final bit will be 1 1 0 1 0 0. Okay, the parity bit can be either in front or at the back. Okay, but you need to write, this is the parity bit, this is the parity bit. Okay, kalau you nak tambah kat belakang, you tambah kat sini. So barulah dia akan jadi 4. So you will have 1 1 0 1 0 0 1. Okay, so now the numbers of 1 is equal to 4. So if this is the situation where you need to check the even parity. if the question asks you about the odd parity, so you will have, for example, the odd parity original numbers is equal to a 0, 1, 0, 0. Okay, the noise or the parity will be at here. Okay, so this is the even parity, still the even parity. All right. I don't have the example for odd parity here. Okay, but this also will be discussed in the tutorial, but you need to cover also until the parity generator or parity checker for chapter 5. All right, I think that's all for chapter 5. Any question?
No.
No? Okay. Is Zahid here?
Yes, madam.
Lisa, Diana?
Yes, madam.
Ada Pergi mana? Keluar ke?
No, no, no.
Are you still there? Iman, Lisa, ada?
Yes, madam.
Alright, so that's the end of chapter 5. Now I would like to brief regarding the lab 4. Okay, so lab 4, I have uploaded the lab sheet for the asynchronous laboratory session 4 in the ULearn, and make sure you also need to click the attendance for section 1. There is no section 1 attendance lab. No problem. Okay, I will take the attendance from this lecture session for the lab session 2, and then you need to submit the lab 4, and then the I think let me see. All right, lab session 4 submission will be due date on Friday 28 May sebelum 12 PM. Okay, tengah hari. So the submission must be submit to the ULearn in a group. So you don't need to submit individually. Just submit in a group, which I think two. You have 2 or 3 per group, right? Okay, so get back to the lab sheet. You can open the lab sheet. Okay, and all right, so the lab 4 will be regarding of the binary adders, with the objective to understand the operation of half and full adders, next to design and construct the circuit of half and full adders, and then the third one is to investigate a two complements adder and subtractor system. Okay, instead of because now we are in the MCO again, you need to use the multisim. There are the multisim live. Okay, I think I have paste the link for the multisim live in the WhatsApp group. You also can use a circuit simulator or logic ly or any suitable tools that you think you are suitable with. Okay, this is the introduction that I think I have discussed in the lecture session. So let's go straight away to the procedure. All right, so part 1, in this lab session we will have 3 parts. Okay, and then part 1, you need to design the circuit of half adder by following the instruction. First, produce the truth table of 2 bits binary with sum and output carry, and then write the Boolean expression and draw the logic diagram, and then construct the circuit and verify the output. So for number C, this is where you need to use these simulation tools to simulate or to simulate the construct of the half adder. Okay, for the number A and B, you can refer to the lecture notes where we have here, for example, okay, let's see the half adder. Okay, yang ni you boleh terus salin. This is the truth table for half adder, and how how you get the Boolean expression. Sorry. And then, yes.
Tak nampak slide.
Oh, sorry. Dari tadi tak nampak
Baru je.
Oh, baru je. Oh, wait Share content. Window. Chapter 5. Oh, sorry Okay. Kalau tadi yang ni nampak? Nampak tak? I punya nampak Okay, so the A and B, you need to produce the truth table using the 2 bits binary of half adder, and then write the Boolean expression, and then this can be take straight away from this slide. Okay, now nampak saya punya slide?
Nampak pun.
Nampak Alright, so number C, you need to construct the circuit and verify the output. Alright, so you need to construct circuit and verify output using the simulation tool. Okay, let simulation tools. Okay, kalau kat sini, let me stop this first. Right, how about here? Can you see my screen? Yes. All right, so this is I use the logic ly as the simulation tool. So you want to design the half adder. We know that the half adder is the combination of XOR gate, XOR gate with the AND gate. Okay, as for the input, I put the toggle switch is for either to see whether this is 0 or 1. Let me open sekejap saya buka balik saya punya ni. 0001. So this is A, this is input A, and this is input B. Okay, switch 1 is input A and switch 2 is input B. Okay, and then we know that the combinational logic gate for half adder will be the from XOR gate and AND gate. Okay, and then for the output you can have light bulbs, okay, just to confirm or just to check whether you get the correct output or not. Okay, so from the truth table we know that saya kena buka dua sorry. So this is our truth table. Okay, when A kosong ialah this is output for some edit truth table. Boleh tulis. sum. Sekejap stop present. Reload. Okay, share again. Let's share here. Okay, sekarang nampak saya punya desktop macam mana? Nampak kan? Okay, so based on because number C just now, you need to construct the circuit and verify the output. How can you verify the output? You refer back to your truth table. So this is input A and this is input B. And you have two output, which is sum and carry out. So and then we know that this is the combinational logic gate of XOR and AND gate, right? So get back to your truth table. When 0, 0, both output are 0. Okay, when A is 0 and B is 1, A is 0, B is 1, only at sum will be light up. Light up means high lah, ataupun 1, ataupun kat sini kita display with what? This light bulb. Okay, when A is 1, B is 0, okay, only at again only at sum will be light up, and then lastly 1, 1 only at carry out will be light up. So this is how you verify your output. So you need to print screen each of these condition. For example, only for example, when 0, 0, 0, 0, both bulbs will be not light up. So next is 0, 1. So print screen this, put in your report, and 1, 0, this print screen again, and then include in your report. Lastly, 1, 1, you will have this final output, and then you need to put in your report. So so that you can verify whether you get the correct output for your simulation circuit or not, right? Next is repeat the same procedure using the full adder circuit. For full adder circuit, we know that you need to have either this combinational logic circuit or this 2 half adder and or gate in order to get the this output to verify this truth table. Okay, so for full adder, I need you to design or to simulate the circuit for both from this circuit. Sorry, first simulate this, simulate circuit 1, and then secondly simulate this circuit. Okay, and then you compare whether you verify whether using both by constructing this both circuit, you will get the same output. Okay, so this is for repeat the same procedure full adder circuit. Okay, next is part 2. All right, so where you need to construct design the full adder by using NAND gates only. Okay, and then for this I think most of you will not get the same answer, because it doesn't matter how many NAND gates you will use for your full adder. Okay, And then you can refer to this this circuit. Either you want to choose the circuit 1 or circuit 2 in order for you to transform into the NAND gates only. Okay, then you can start by modify the Boolean expression and modify the existing circuit using the dual symbol method, and then construct circuit and verify the output using the simulation tools. Okay, and then I think for part 2, number 3 and number C, you can refer to the chapter 5, chapter 4, part 2. Okay. And lastly, you have the arithmetic operation. Okay, use a suitable table to record the observation for all of the inputs and output of the IC. Write your discussion and conclusion. Okay, so only for part 3, you didn't have to do the simulation. So you need to use the suitable table. For example, you have this is how I show in the this kind of adder or the subtraction. Right, for example, you have plus 5 to be added to the plus 4. Okay, so you know that it will be the 4 bits. Okay, and then 4 bits mean you will have 5 5 sum. Okay, 5 sum with C5 will be equal to sum number 5. So binary for 5 will be 0101, and for 4 is 0100. So C in is here, C in is equal to 0. Okay, so what is the output for the sum number 1? 01 is 01 is 1, 0 and 0, 0 and so on. Okay, and then lastly you will get the carry. So you can answer, or you can do the calculation in kind of this table. Okay, so for the number B and C, it will number B, number B is the complement for 5. You need to add minus. Okay, you need to use the complement in order to get minus 5, and then number C is the subtraction. Okay, for the subtraction in the ULearn, okay, I include, can see week 11. All right, so I include the supplementary notes for the subtractor. Okay, you can refer to this website in order to answer the question in part 3, number C. Okay, any other question? I think that's all for the lab session 1. And then you need to do the simulation, and then the report must be hand in before Friday 12 a.m. Can I know Nurul Kamar ada tak dalam ni? Is Nurul Kamar here? Nurul Kamar dalam section 1 kan? Shakilah, can you confirm that Nurul Kamar is in section 1 or not? Kan? Is she here? Kamar, are you here? Tak ada. Laili? Is Laili here? Tak ada. Laila ada, Laila?
Ada.
Oh, Laila ada, Laili tak ada So, okay, saya akan try to figure out where these two students. Alright, so I think that's all from me. Make sure you, if you have any question, you can direct us in the WhatsApp group or PM me. Alright, thank you very much for your time, and I hope you can submit the report in the given time. And please be, I want to, your submission for assignment will be in 1st June. So make sure if you have any question regarding the assignment ataupun apa-apa. Untuk assignment, I have create the forum in the Ulearn. If you have any question, ask there. I will reply there. And that's all from me. Thank you very much, and Assalamualaikum warahmatullahi wabarakatuh. Have a nice day and stay safe.